Hello everyone, this is Enchang Dai from Puget Sound Energy. I'm very happy to be with you today to talk about the graph database and the graph computing for power system transient simulation. Power system transients involve large-scale, high-dimensional differential equations and algebraic equations. Differential equations represent the dynamics of units, exciters, PSS, and governors. Algebraic equation represent the network. Once we know the injection currents from units, we can calculate the bus voltage. And the current injection is a function of voltage and the state variables. DAEs has been developed for decades for power system transients. They are still with us. However, we are still on the way to achieve faster than real-time simulation for large-scale power systems. By using graph computing, we think it's a promising way to achieve the goal. In power system transient simulation, there are two methods to solve the transient problems. One is an integrated method, another is a sequential method. We are using sequential method to solve transient problems for a couple of reasons. Number one, in sequential method, we solve algebraic equation first to get the bus voltage. Once we know the bus voltage as a terminal condition, as a boundary condition for units, we can solve differential equations and calculate the current injections to current. Then this updated current will use to update the bus voltage until voltage is converged. So it provides a good opportunity for us to leverage the powerful graph computing experiences on solving algebraic equations as we developed for steady-state applications years ago. And also gave us a chance to develop a fine-grained graphic parallel computing to solve differential equations and calculate the current injections. Because once we know the terminal voltage of the units, think about it if we have 1,000 units in the system. Once we know their terminal voltage, we can solve the 1,000 differential equation sets and calculate the 1,000 current injections simultaneously in parallel. So that's the beauty. Gave us a great opportunity to use graph computing for DAE solution. Before I talk about how to use graph computing to solve transient problems, I wanted to spend a few minutes using the following a couple of slides to talk about the graph database. Graph database and graph computing are widely used in large spectrum of disciplines, covering social network in IT industry, transportation network, financial systems, and power systems. To highlight the benefits of using graph database for power system modeling, I wanted to compare the way we model power system by using graph database against the way we are using relational database for power system modeling right now. So in relational database, we are using tables to model power systems. We use a unit table, transformer table, node table, transmission line table, bus table, so on and so forth to model power systems. They are in silos. So we have to use bridge tables to describe the connectivities and the topologies of power systems. So it's kind of a conversion translation process. You have to translate the physical power system to tables. Then you do your calculation on tables. Then you remap the result back to power systems. So this pre-processing and post-processing introduce additional efforts and simulation times, slow down the computation efficiency. The reason we wanted to use tables because we are familiar with using tables to do power system calculations. But it's really hard to use the structured tables for parallel computation. In contrary, if we use a graph database, we model the power system by graph because naturally, physically, power system is a graph. Buses are connected by transmission line and the transformer. So if we model power system by graph, do the computation on graph, and do the display on graph, that can save a lot of time of pre-processing and post-processing. It enables us to do the parallel computation as well. So we use this testing to test the performance efficiency of database operation by using relational database and the graph database for two different sizes of systems. One is 2643 bus systems, another is 10,790 bus systems. We tested the common used operation for database, include searching, ordering, inserting, deleting, and topsy. For all of the operations, graph database is outperformed than relational database. Some of them are slightly faster. Some of them are really dramatically faster. For example, for searching, graph database is 40 times faster than relational database. Those operations are widely used in power system applications. With that, so I wanted to talk about how we can use the graph computing to solve algebraic equations and the differential equations. For algebraic equations, for example, for solving power flow, basically what we are going to do is, number one, we needed to form Y matrix. Then we needed to do the symbolic factorization to understand the fill-ins. Then we will do the numerical factorization and the substitutions. For Y matrix formation, it's quite easy and straightforward to perform parallel computing because form one node admittance, you don't have to wait other nodes to finish their job. You can do them all together by using the queries. So using graph computing is different from traditional way we do the calculation. We use queries to perform the computing. So for admittance matrix formation, we can use nodal parallelization to perform the computing. But for factorization and substitutions, because naturally their calculations are dependent from one node to another. However, it's not fully dependent. One node calculation is dependent on just small portion of the total nodes in the system because it's sparsity of the power systems. So we use the elimination tree to determine the dependency. For example, for these 10 bus systems, once we build the elimination tree, all leaves at the same level can be eliminated at the same time in parallel. Once they are eliminated, the next layers, nodes, or leaves, their calculation are no longer dependent on any other nodes, so they can be calculated independently in parallel. So on and so forth. By using the algorithm 1 to 5, we can build up the Y matrix and do the factorization. By using algorithm 6 and 7, we can do substitutions to solve bus voltage. We use this method to test on two systems, 2600 system and 8500 systems. They are large systems. We use the graph to model the system just as we show on the page. The orange line represents the edges and the blue dots are vertex. For this large scale system, we have 400,000 vertex and 1.7 million edges. It's a large system to model all devices, stations, nodes, bus, breakers, and measurements. It's a large graph. However, the computation is very fast because we are using parallel computation. For 2600 bus system, it takes us 75 milliseconds to finish the power flow. For 8500 100 system, it takes less than 100 milliseconds for power flow solution. Moving forward, we use the parallel computation by graph to solve DAEs for transient simulation. So here is this flowchart to talk about how we do the transient stability simulation using sequential method. So basically, the first thing we do the initialization using power flow solution. Once we know the bus voltage and the reactive power, active power of generators, we can initiate the state variables. If the topology changes, we need to reform and refactorize the Y matrix by using algorithm 1 to 5. Then we can calculate the bus voltage by using algorithms 6 and 7. Once we know the bus voltage, we can solve differential equations and calculate current injection by using algorithm 8. I will talk about it later on in parallel. So we do this loop until voltage is converged. Then we move to the next step. So in algorithm 8, it's parallel computing for numerical integration. Basically, what we do is we use the selection queries and use accum and post-accum. Those are special keywords for graph computing. In accumulate, what we do is in the nest of the accumulate, all of those calculations are calculated in parallel for equation 1 and 3 to solve a dynamic equation in the current injection. Once we know the injection current, in post-accumulator, we will solve algebraic equations by using equation 2. By using the parallel computation, graph parallel computation, we developed for power flow. So using this way, we test on a real system and IEEE standard systems. For IEEE 9-bus system, 36-bus systems, and 2 large-scale systems. Using the small system, IEEE standard system as a benchmark, we test the accuracy of the method to make sure the results are inconsistent. Using a large-scale system, we can test the performance of the graph computing. For the 10,000 bus system, we have 40,000 differential equations and 21,000 algebraic equations. So it's a large-scale, high-dimensional DAEs. So in the simulation, at 2 seconds, one of the bus occurs 3-phase to ground fault, and at 2.2 seconds, the fault is recovered. We simulated the transient for 20 seconds. It takes 33 seconds for 26 bus system by using graph computing. And it takes 122 seconds by using traditional method. For 10,000 bus system, it takes 46 seconds by using parallel computing and 175 seconds for traditional method. The speed up ratio is up to 3.8. This is a preliminary result. So it's still not faster than real time, but we have a potential, we have a big room to move forward to achieve faster than real time simulation. Conclusions. High performance computing is critical if we wanted to achieve faster than real time transient simulation. And graph database enable us to model power system more straightforward and naturally. Graph computing opened a new way for us to solve a power system in parallel. After several years practicing and experiments, we built up the confidence and had a good position to move forward, touch other power system applications such as the security constant unit commitment, economy dispatch, OPF, and the electrical magnetic transient. Thank you.